Proper time. Einstein abandoned the common-sense notions of absolute time and absolute space. These are merely relative quantities that can stretch and contract. However, without absolutes, we cannot describe reliable physical laws, such as velocity and acceleration. We have already obtained an invariant quantity called ds squared. To describe velocity and acceleration, we need a time that has physical meaning for everyone, an invariant time. What Einstein adopted is your subjective experience, your consciousness, your sense of being here and now. We attached a clock to each of us as the origin of coordinates, not just to living beings, but to every entity in the universe. Einstein established this as proper time, which is unique to each observer yet remains a physical invariant. Think of yourself as the origin of a Minkowski spacetime diagram. Imagine a VR game. No matter how many thousands of kilometers you travel in the game or how vigorously you move around, you are always at the center of the screen, at the center of your perspective. Your viewpoint does not move anywhere. It stays with your existence. The real world works exactly the same way. Whether you take a 100 kilometers car journey or fly through space in a rocket, your perspective was always with you. In your own rest frame, the origin is you, and your displacement in the spatial direction is zero. Einstein incorporated this subjective experience, each individual's personal experience, into physical theory as the invariant physical quantity called proper time. Physics incorporating subjectivity? This may seem strange, but this idea has been confirmed through numerous experiments. For example, GPS satellites and the ground have different proper times, but by correcting for this difference, we eliminate positional errors. This is verified every day. Now let us examine proper time in mathematical terms, this time measured by each observer on their own clock, which has invariant physical meaning. We express the space-time interval ds squared in two inertial frames, the moving object's rest frame and the stationary observer's frame. In the moving object's own rest frame, primed coordinates, the object has zero spatial displacement. dx prime equals dy prime equals dz prime equals 0. Therefore, this equation expresses the moving object's proper time dt prime in terms of the stationary observer's coordinates, ct, x, y, z. We denote this dt prime as the proper time d tau. Both c squared and ds squared are invariants. Therefore, tau, as the ratio of invariance, is also an invariant. We substitute the Minkowski metric into ds squared. We will use this equation much later. We will find the relationship between proper time and relative time. Let us transform the equation for the invariant ds squared. Divide both sides by negative c squared. Factor out dt squared from the right-hand side. Since dx squared over dt squared plus dy squared over dt squared plus dz squared over dt squared equals v squared, we obtain the following equation. Taking the square root of both sides, the reciprocal of gamma appears. Since gamma is greater than or equal to 1, this is less than or equal to 1. Let us examine the meaning of this with specific examples. Suppose 10 seconds have passed in the stationary frame. Let the velocity be 0.6 c. When 10 seconds have passed in the stationary frame, only 8 seconds have passed in the proper time frame. The crucial point: in the equation d tau equals 1 over gamma dt, d tau is the moving object's proper time, expressed in terms of the observer's coordinate time, dt. This shows that the moving object's clock runs slower. Now let us increase the velocity to 0.99 c. When 10 seconds have passed in the stationary frame, only 1.4 seconds have passed in the proper time frame. This means that the greater the relative velocity, the slower the proper time progresses in the moving frame. From d tau equals 1 over gamma dt, we have d tau less than dt. Maximization of proper time. Every object in this universe moves in various ways within its own proper time. Some undergo accelerated motion, while others move at constant velocity. Among the various paths connecting 2 points in spacetime, we will see that objects in uniform motion, including rest, have the maximum proper time. Consider 2 points A and B in a CT-X spacetime diagram. We draw the trajectory of a free particle in uniform motion as a red line. We represent the trajectory of an accelerating particle as a blue line. Now let us ride along with the red free particle and see things from its perspective. Just like the VR game we discussed earlier, you are always at the center of the screen, at the origin of the coordinates. When we redraw the coordinates in this particle's rest frame, CT prime x prime, the red line becomes a vertical straight line. The particle remains at position x prime equals 0, and only time CT prime progresses. Let us verify this with explicit equations. The proper time between events A and B is expressed in integral form as: in the rest frame, CT prime x prime of the free particle, the particle does not move in the spatial direction, so v equals 0. Therefore, the square root of 1 minus v squared over c squared equals 1, and the integral reaches its maximum value. For an accelerating particle, v does not equal 0 at some point, so the square root of 1 minus v squared over c squared is less than 1, and the proper time becomes smaller. Therefore, among all paths connecting the same 2 points, the particle undergoing inertial motion, uniform motion including rest, has the maximum proper time. The twin paradox. Let's examine the famous thought experiment known as the twin paradox. There are twins A and B. Twin A stays on Earth, while twin B travels through space in a rocket and returns. Both possess their own proper time, the VR game perspective. From each twin's viewpoint, they themselves are not moving through space. The other twin is moving. Now let's consider how each twin views the other's proper time. Recall the equation d tau equals 1 over gamma dt. This shows that the moving person's proper time clock runs slower. In other words, time flows more slowly for them. From A's perspective, B is moving, so B's proper time runs slower. From B's perspective, A is moving, so A's proper time runs slower. In other words, each twin believes they have aged more than the other. Here lies the paradox. Now let's resolve this paradox. Let's examine the spacetime diagram of twins A and B. Twin A remains stationary on Earth, inertial motion. Meanwhile, twin B must turn around, accelerate, at some point to return to Earth. Recall the property of proper time. An object in inertial motion, constant velocity, or at rest experiences the maximum proper time. Therefore, more time has passed for twin A on Earth, and A has aged more. Let's verify this with an actual calculation. To calculate the twin paradox concretely, we use a simplified model where twin B's motion follows a sinusoidal curve, x equals L sine of ct over L. This model makes the calculation straightforward while preserving the key physics of the paradox. The calculation of proper time for twin B and twin A is shown here. Please pause and work through it at your own pace. The ratio of their proper times approximately equals 1.57. Twin A ages approximately 1.57 times more than twin B. Concrete example: if 10 years pass for B, then 15.7 years pass for A. Summary of proper time through the twin paradox. Let us summarize proper time while touching on the twin paradox. Proper time is the time measured from a perspective like that of a VR game. In relativity, it is the time recorded by a clock that travels together with the observer or the object being observed. From the observer's own perspective, there is no spatial displacement, only movement along the CT axis. Now, there is no absolute rest frame in this universe. When you're observed from outside, you are moving both in time and in space, even though the external observer also has their own proper time and is at rest in their own frame. Compared to the coordinate time dt of a stationary external observer, the proper time d tau of a moving observer satisfies d tau equals 1 over gamma dt. Gamma is greater than or equal to 1, giving d tau less than dt. This means the rate of time progression is smaller. This is the true nature of time dilation. Here, a contradiction seems to arise. Proper time is an invariant. So how can the proper times of two observers differ? However, there is no contradiction. The proper time of each twin is unquestionably an invariant. The proper time tau A of twin A yields the same value regardless of which frame it is calculated from, and the same holds for tau B. This is expressed as. Let us look at a concrete example. The calculations showing that proper time is invariant are displayed here. Please pause and work through them at your own pace. Note that case 3 does not yield an invariant result. We will explain why. This does not equal 10 years. This is because the acceleration at the turning point has been neglected. A rigorous treatment, accounting for acceleration yields, tau A equals 10 years. So why does a difference in proper time arise between the two? It is because twin A, remaining on Earth, undergoes inertial motion, and inertial motion maximizes proper time. Twin B, on the other hand, accelerates and decelerates during the rocket journey. As a result, less proper time elapses for B, and when the twins reunite, B is younger than A.